Alright, so the first circuit element that we're going to work with is a capacitor. And so just to remind ourselves, the basic question of what is a capacitor can be answered a couple of ways. And the first way is it's a device for storing energy in an electric field. Now you can build a capacitor by basically taking two conductors, putting charge on them, and then separating them by vacuum or insulating material. That's going to form a capacitor. So basically what we're going to do is we're going to deal with situations where we take some charge, put a positive amount of charge on one conducting plate, put a negative amount of the same charge on a second conducting plate. Separating those two by a certain distance will ensure that there's a potential difference between those charges, or between those plates. And so with a capacitor, the amount of charge on the capacitor, how that relates to the potential difference, is defined by this equation. So for starters, C here is the capacitance. That's the fundamental quantity of a capacitor. Okay? What we're going to do is we're going to, instead of writing delta V, we're going to choose to write V, but we want to recognize that, again, that's just the potential difference between the conductors. So that's when we talk about the voltage across the capacitor or the potential of the capacitor, really what we're talking about is the potential difference between those two plates. And then when we say the capacitor has charge Q, or there's charge Q stored on the capacitor, well, really what we're talking about is just what's the value regardless of sign. So you can think of basically what we're saying is what's the charge on the higher potential plate. Now obviously if we've got positive Q on this plate and negative Q on that one, well, you add that together and you get 0. So stored across our capacitor is actually 0 net charge. So when we talk about the charge on the capacitor, again what we mean is, well, what's the charge on either plate regardless of sign. So basically what this means is that we have a definition of capacitance. So if we rearrange that equation, we can solve for the capacitance as it's the charge on our plates divided by the potential difference between them. So what this is telling you is basically the capacitance is a measure of how much charge you can store at a given voltage. So for a certain capacitor, it has a certain capacitance. That capacitance basically says if you have this large a potential difference between your plates, then you can store this much charge on those plates. So if we look at this equation in terms of units, again we see that the units of capacitance are nothing more than the units of charge, that's coulombs, divided by the units of potential, that's voltage. So coulombs per volt is one way to think about the units of capacitance. The SI unit we most commonly use is known as the farad, and again this may seem like a very strange word, but it's really just short for Faraday. So Michael Faraday was one of the big discoverers with electricity in the 1800s, and so the farad is just just sort of a name we've come up with as a tribute to him for what he did within the field. So farads will be our units for capacitance. Now again, how do we sort of store this energy within an electric field? Well, let's start again with our two plates, but this time let's start with them being uncharged. And so what we can do is we can slowly start to bring charges in to charge these plates up. Now you notice in this situation, my two plates happen to be parallel to each other. So it doesn't matter whether these are circular plates or rectangular plates. The important thing here is that they're parallel to each other and they're separated by some distance d. So I can calculate the capacitance for any parallel plate capacitor by taking here's our constant again of epsilon naught, the area of the plates divided by the distance between them. So you'll notice that what the capacitance depends on, or what the capacitance cares about, is just the geometry of the capacitor that you've built. So you've built plates with a certain area, you've separated them by a certain distance. That's actually all the capacitance cares about. So then what you can do is you can start bringing charges in. And again, as you can think of it as, as you bring in electrons from this side, right? We know electrons are what we're really moving around in our circuit. So if I were to bring an electron into this plate, that would drive an electron out over here, leaving it positively charged. Again, I keep building up more and more over here. I keep driving more and more electrons away over on this side. And so what I'm left with is a positively charged plate and a negatively charged plate. And I know if I've got a positively and negatively charged plate that's going to build up an electric field. So at the end of the day, the work I'm doing in moving around these electrons to store them on the plates as charges generates an electric field. And so that's where this energy is being stored. And as we'll see, we can get that energy back by discharging the plate. So this is fundamentally how a capacitor stores energy within an electric field. It takes work to charge these plates. That work is being stored as electrical potential energy within the field. So if you wanted to calculate how much energy you've stored within a capacitor, well, here's the equation that we'd use. So again, you have an electrical potential energy that's going to be equal to 1/2 the value of the capacitance times the potential between your plates squared. Now again, we know that we can write Q equals CV, and so we can use that relationship and basically say, oh, well, C times V, so if I take 1V out of the V squared, multiply it by C, that's a Q. So I can rewrite the energy stored as 1/2 QV. Or I can rewrite it as 1/2 Q squared over C. Again, just sort of continuing to use my Q equals CV equation. We'll see that basically that's Q equals CV is sort of the fundamental equation describing what goes on with a capacitor. And so it and this expression for how much energy is stored within a capacitor are the two really important relationships that we'll deal with when dealing with capacitors within circuits.